So this week I'm going to do recorded lectures because, well, we had last Friday off, and we're going to have next Friday off. This Friday we're scheduled, but this Friday I'm going to do the makeup test for those who haven't taken it yet during class time. Please email me at michael.littlecrow@gcu.edu if you are planning to take the makeup test, so I know who's to expect. So please do that part. Otherwise, today we're going to look at 18.1 and 18.2. By Friday, I will have 18.3 and 18.4 lectures up and running, so you can go through those. But they're each bringing in concepts of vectors that we've done and parameterized curves that we've done. So it brings a couple different concepts together. Okay, so let's go ahead and get into today's lesson, 18.1 and 18.2. And then we just have one more chapter, a couple more weeks after that, and then the final exam. So we'll get focusing on that. I'll make the practice test available soon, as I'm going to take a look at those problems and narrow things down a bit. Okay, so what is a line integral? Okay, we've been thinking of line as area under the curve, but what exactly would be a line integral? Well, a line integral kind of is using this concept of an integral to follow a curve with integration, getting the path in a vector field. Okay, and so what we do is we don't just get the vector r that comes off. So there's a vector field. So we've got these over on the right hand side here. We see what the vector field would look like, and then we see along this path, and by taking the vectors, the difference of the vectors at various points along this path, so we take vector r sub 0 minus r sub 1, and what we get is we get a vector that is really following the path. And so that gives us a result that we're going to be able to use for what is the work along a path, what is the effect of this vector field, which could be some kind of a force like gravity, other things, wind. So it's the force imposed on something while a particle or something is moving along a particular path. So that's what we're looking at, and we'll look at some details. And again, we get this idea of an integral is the sum of the various force of the vector in the direction of the path. This change in r kind of directs it along the path and finds the component of the external force that is working in the direction of the path or against the path. And so we can see, and again, if we go with the path, we end up with a positive, or that the force and the path are working sort of together. We get a positive value. When we work against it, we would get a negative value. Okay, so we're going to compare a few things here. Okay, here we are. So first of all, we're given a vector field, so we've got some kind of a circular, maybe we're inside a tornado, it looks like. And we've got these oriented curves, C1, 2, 3, and 4, and again, they could be objects that are traveling along these paths. And so then we want to see which of these integrals would be positive and which would be negative. And then we'll want to arrange them in ascending order, so from smallest to largest. So first of all, we see C2 is going in the direction of the arrows, so that'll be positive. C3 is going in the direction of the arrows, that'll be positive, and C1's in the direction of the arrows. The only one that's going against the arrows is C4. Unfortunately, it's inner, where these the force is smaller, so that's probably what allows it to do that. So C4 is a negative So which are positive? C1, 2, and 3. And I'll just do it like that. Which ones are negative? Well, there's only one, C4. So if C4 is negative and all the rest are positive, C4 is the smallest. Okay, so ascending order, we've got C4. That's the smallest one. And then we start looking at the size. Remember, these paths are also sort of vectors, so their size gives us an indication of the path and sort of the magnitude. C1 and C3 are roughly equal, but we can see that with them being equal, the forces on C1 are smaller than the forces on C3. The vector field has more magnitude out here. That's going, and because it's a multiplication thing here, right? The vector field times the change in R, so we're multiplying. So it's about equal in size for C1 and C3, but the vector field itself for C3 is larger. It's going to give a larger value. So the next one that would be bigger is C1 and then C3. And we haven't looked, but we would have to also talk about C2 if you wanted to. It's larger, and it's about the same level where C3 is as far as the vectors, the magnitude of the vectors here. So it's larger than C3, and it's going to have the same multiplier, the big F, the vector force field of F. So C2 is going to be the largest. Okay, we don't have to wait to calculate it, but that's how I would talk through it. Now, I'm going to show you the slide where they have it in written language, and they talk it out. So vector field line segments are approximately parallel, so they're going the same directions for C1, 2, and 3. So they're going to be positive because they're going with the flow. Okay, so the force vector is a positive direction, giving them more power. The curve 4 again is the one that's going against the flow. It's having to do more work, so it's going to be negative in response to the field it's going against. Maybe opposite is a better thing than negative, but that's what we do it as. Let's back up. And the original one had it had C2 here, but you can see that C3. So the product is smaller, and they explain it here that these two curves are about the same length. So it explains what we did. The force here in C1 is smaller than C3. So the integral with C3. Now, I guess my notation was I was saying that I was comparing just the values of C, but really what I was comparing is the overall result. Okay, so I knew they were going to do this. But that's the result of C4 is obviously the least because it's negative, and we've got C1 which is less than C3, and C3 is less than C2. Okay, so they put all that together. So some of the activities will have you do that, looking whether it's positive or negative. You don't actually calculate, you just use those principles. Okay, let's talk about work. This is actually excuse me, this is a homework problem, so we're going to look over this one. The work done by a force along a curve is the sum of each function value at a particular value times the change, okay, which gives us this integral over the span. And so we've got this problem. We've got the path here going from 0, -1 to 4, -1, and then going up to 4, 3. And we've got this force vector here, y I plus x squared j. Okay, so how do we characterize this one? Sorry, I was pointing in the wrong place, I think. Anyway, we got this, we're going here to here, and then up. So let me let's keep those for now. I knew I was going to need more room. We're going to come back to that problem. I'll go ahead and do this one, then we'll come back and do a few others. Okay, so since we started this, maybe I'll make this a little bit smaller so we've got some room to write. So first of all, to get, and I actually forgot to write or copy in the B part of the question, but I'll go ahead and do that. So the first part asks us to evaluate I don't know why it does this. That down, minimize, and then I want it draw. Let me pause this for a moment. Sorry, folks. Okay, now we're back. So we want to evaluate the function, the force at each of these values. So that's one thing we do. Basically, we just insert the x and the y into the vector. So you can do that. So thinking of it as a function 0, -1, we're going to put in, and we've got this I, so j or y, so -1 I part plus x squared, which would be 0 squared j. So the resulting vector is -1, 0, or just -I. And then you could do this for each of them. I'm just going to jump ahead a little bit here. We'll do 3 -1s to show you how that works. So again, the y vector is still -1, the y component, and then the x component is 3. So we get 3 squared, and that's going to give us the force in the y direction actually. So we get -I plus 9j. So that would be our vector. And we could do that with each one. We're just plugging in the points. Now when it comes to work, well, let's look at this. This force vector, when we're moving here, the vector all along here from 0 to 4, it's only moving in the x direction, so that's the only part that does it. This j direction is perpendicular to it, so it doesn't have any effect on on the work that's being done. So moving in this x direction, the only force we need to consider is -1 I. Okay. And we need to do it at each of these points actually. So we're going from 0 to 4, so the length of this path is 4, and the force against it's -1. So the work from 0, -1 to 4, -1 is going to be -1 times the length, which is 4, it gives us -4. So that's the amount of work along this part. It's actually going against, so the work is negative. So going up, notice the x no longer changes, but x is always 4, right? So it's a constant amount, and since we're going up, the only thing we need to consider in that case is the y component, which is x squared j. So then we just going from work from 4, -1 to 4, 3. Again, the length of the path is going to be -1 to 3. That's still 4, right? That's the length of the path. We put that there. And what is the force of this of the vector? Well, it's x squared j. So we put in, well, x squared is going to be 4 squared. So our vector in that direction is going to be 16. That's 4 squared j, positive. Okay. And so we're going a length of 4 times a force of 16, and it's an increasing force, and we're going up. So 16 times 4 is 64, and we add these two. This is the total work that's been done, so we add these two together and we get 60. Total work. Okay. So while we're here, I think there's one more slide to review on properties, but let's look at a couple here. So say whether you expect the integral of the pictured vector field over the curve to be positive, negative, or 0. And again, they may give you something slightly different. It might be the same, but look at we're moving this way. So think of it, this first part is going to be negative. It's moving against the vector field, and then it's it's certainly not going with the vector field, so it's for the most part negative. Over here, whatever the vector field is, it's kind of coming down on it. It's starting to go positive. So what the thing is we've got symmetry between this half and this half. So they're going to cancel each other out. So it would be very easy to say, because of the symmetry, this is going to be pretty much negative, this is going to be pretty much positive, and the vector fields are looking the same in both sides, so we would expect 0 to be the net result. And that's what the answer was. Okay, so something like that. Here we go, we're asked to calculate the line of integral of the vector field here along the line between 0, 2, or 0, 2, 0, and 0, 0, 0. Notice the only thing that's changing is the y values. That's really all that's that we need to, because the x and the z are not going to be there. So one way we can calculate this is the integral of the vector field. And again, since this change is in the y direction, that's all that's going to change. The x and the z direction don't change. We're going from 2 to 0. So notice the direction. Usually we put the larger number on top. You could do that. You could go from 0 to 2 and call it negative. I'm just going to show you we're going to get a negative value. So because this is the direction we're going. We're going from 2 down to 0 in the y direction. And what's the y direction? It's 5 dy. Okay. So times the change of y, right? So we integrate this. That's going to give us 5y from 2 to 0. And then we plug in 0 first. So we go 5, 0 minus 5 times 2. It gives us 0 minus 10. So negative 10 is our answer. And we'll see the force times the change in r is negative 10. One way to do it. Now if x and z were changing as well, we would have those components in there, but so this is a more simplistic case. Okay, so we got that. We did that first one. We did this one. So let's finish up this little section here in the PowerPoint with a slide on the properties. And it just shows us it works like other integrals we've done, over this circuit. So if we've got we multiply by some constant, Lagrange multiplier, if you want to call it that, you can take it outside. Constants come outside. If you're doing a sum, you could do the sum separately. You could do the integration, two different integrations, add them together. It's the same as adding them together and doing the integration. And when you go from, the negative direction of the path, we could have used this property on the last one. I just went from 2 to 0 instead of 0 to 2, make it negative. But when the directions are opposite of each other, that's what happens. Okay. And finally, if you have two different paths that are being added together, you can also do it as two separate integrals. And we've done that kind of before because the limits could be different, right? And so you integrate and you find the two different limits and you add the results together. So those are just some properties of line integrals that are consistent with the other types of integrals we've done. So now we're going to look at a few examples of computing line integrals over parameterized curves. I apologize, I do have a difficult time saying that word. Parameterized, maybe that's it. So here's an example, and we'll work through this one. But the main thing we're going to use is that we're coming back to that over a particular path, C, a vector field times this. This is going to give us the result. And what we can do is we can actually parameterize it with another function. And we typically will do this to make it easier to integrate. And we're going to see in the last slide that as long we can parameterize it any way we want, as long as it all fits, so we do it the right way, and we'll get the same answer. So let's look at this example and we'll kind of see how we do it. So we've got this quarter of a circle here, and we want to find along this path C, which is going from 0 to pi over 2 if you want, in this quadrant here, against this force vector field, x plus y, I plus ij, quarter unit circle. And okay, so that's important. It's a unit circle, so it's only got a radius of 1, and it's oriented counterclockwise as shown, so it's kind of fighting some of the curves anyway. And we're going to parameterize it with this. Let's I'm going to keep this stuff, and then I knew I needed more room, so what I've done is I've copied it to here, and we're going to go along and we're going to parameterize the path with a function. And since it's a circle, one that might come really well to mind is that we could set x equal cosine of t, some new variable, and y equals sine of t, theta if you want the angle as we come through here. And as you see, since it's a quarter circle, we're going from 0 to pi over 2. T will be from 0 to pi over 2. I think that's pretty much it. And then what we're going to need to do now, so we've got this function, we need derivative. So any point along here, the x cosine of t, y sine of t, so then we can think of this path C actually as being a vector, and that's what we call the R. And that would be the x direction is cosine of t, I plus sine of t, j. And what we really need is we need this derivative. So dr, derivative of cosine is minus sine of t, I, and derivative of sine is cosine. So that's our dr. Our function, x plus y I, so that's going to, we're going to use our parameterized cosine t. So f is now going to become equal to x is cosine t plus y, which is sine t, and that's the I vector, plus just the y times j, which will be sine of t j. And so we're going to be asked to compute over this curve, and since we've got the parameter of t, we're going from 0 to pi over 2. The vector field that's been parameterized, so cosine t plus sine t, I guess I could put another I, plus sine t j, that's the f vector, right? And we need to dot product it with the derivative of the path, and so that's minus sine t I plus cosine t j, and I guess dr. That's what dr is. And now I guess this is, everything's in terms of t, so we'll integrate at the end. I guess that's what I needed to put here, is really, I took the derivative of t. So that's what dr is, that dt. So now dot product. Now remember, with the dot product, we multiply the x components and add that to the multiplication of the y components, or the j, I and j, x and y. So we get cosine t plus sine t times negative sine t. So this is going to distribute here. Maybe I'll do it in 2 steps. So we'll go sine t minus sine t times cosine t plus sine t. So that happens, plus this part, the multiplication here, which is sine t times cosine t. And I'll just leave the parentheses off. It looks a little messier if we don't. So we're going to integrate from 0 to pi over 2 dt. Let's distribute this and then combine like terms and see where we're at. So negative sine times cosine gives us a negative sine t cosine t, and then we get a negative sine squared t plus sine t cosine t dt. Now minus sine t cosine t and plus sine cosine t, these guys subtract from each other and make 0. So now we've got an integral with minus sine squared. So we've got to integrate that. So we look at our trig identities, and the one we want to use is something that doesn't have us, to integrate this. We're going to use the trig identity that sine squared x, t, is equal to 1/2 1 minus cosine of 2x. So, for the test, I'll let you use your notes, so it'd be good to have some trig identities as we work through these. Okay, so now what we have is we have the integral going from 0 to pi over 2. We'll put the 1/2 out front, and that's negative, so negative 1/2 1 minus cosine of 2t. So that's what we need to integrate, dt. When you integrate 1, you get t, so we get a negative 1/2 t minus cosine of 2t integrates as sine of 2t over 2, and so it would be negative. And then what we want to do is we want to take this from 0 to pi over 2. So that's the integration. We could go ahead and distribute, or we can distribute at the end, but notice when we plug in 0, we get 0t. When you plug in 0 here, sine of 0 is 0. So we get to not have to worry about this. We just have to plug in the upper end. So we get minus 1/2 pi over 2 minus sine of 2 pi over 2 all over 2. And again, the 0 part you would subtract off, but we would be subtracting 0. So now sine of 2 pi, so the 2's cancel. Sine of pi actually is 0, so this is 0, so we just got pi over 2 times negative 1/2, which is negative pi over 4. And that is our final answer for that one. And this is the solution as provided by the textbook. Again, the parameterization used was cosine t for x and sine t for y. And going from 0 to pi over 2. When we do that, the force vector, the force field, force vector, vector field, whatever the proper words are, becomes this vector. We take the derivative of the path vector to get our dr, right? And so then we take the dot product between the vector field and the parameterized derivative. There it is. They get this, and then they jump. They said, okay, how do you got to look this up maybe. How do you integrate sine squared t? You can't do it directly. They don't show all the steps in between. This was probably the more important part. And then if you need to, if they'd asked for it as a decimal, you just take pi divided by 4 and you'll get the approximation. So that's how we can use parameterization. Now the next slide is going to show that we won't go in great detail, but what it's oh wait, I'm in the wrong. That's right. We got this one. I've got one more example to look at. So in this one, we're okay. So we've got a vector field, whatever vector field I, j, and k. So a three-dimensional vector field, and an oriented curve we've been talking about. The same thing applies. Vector field times the oriented curve. If they give it to us as this derivative. Notice it's the derivative in the x direction, y. So it's pretty much just a generalization of what we did with two variables, x and y. Now we've got a z1 in here. And so now we're asked to evaluate this integral along this segment 0, 0 to 2, 6. So we'll again use parameterization. So one parameterization, notice x is going from 0 to 2. We could let, let's back up. I thought I had this. It's going to get, well, let's see if it'll let me write. We could let x be equal to t. And if x is t, that gets us from 0 to 2. Y has to go from 0 to 6 with t being the same. So if t was, say, t is 2, so t goes from 0 to 2, how can we make the y part go from 0 to 6? Well, then what you want to have is that y is actually going to be equal to 3t. So that when t is 2, we're at 6, and when t is 0, we're at 0. Okay, so that's kind of how we've parameterized with x and y, and then we can let t itself go from 0 to 2. Okay, and how can we evaluate this? So we go from 0 to 2. We plug in our parameterization, so we get x is t, y is 3t. So we're going to go from 0 to 2, t times 3t dt. So notice, actually, I guess we got dx equals dt, so that's okay. But when we get to y, dy is equal to 3 dt, so we need to make that substitution. So that first part's okay, t, 3t dt, because dx is equal to dt. And then we're going to subtract, well, what's y squared? Y squared is 3t squared, so that's 9t squared times dy, but dy is 3 dt, so we have to multiply by 3 dt. Okay, and so that's going to give us negative 27. And I think this is all kind of worked out for us. So we'll just click here. Oh, no, it wasn't. So I can. Sometimes I'm not quite clear what I copied in that. So let's go ahead and work it down, and it'll show us everything again. So this gives us 3t squared dt minus 3 times 9 is 27t squared dt. So that's 3t squared minus 27t squared. It should be minus 24t squared dt, 0 to 2. And when you integrate that, you should get t to the third divided by 3, and the minus 24 is there, right? And so 3 goes into 24 8 times. So we end up with our final answer being minus 8t to the third, going from 0 to 2. At 0, it's 0. At 2, 2 to the third is 8. 8 times 8 is 64. We should have a negative 64. Let's see if I did it all right. Yeah, we ended up. I didn't look too closely at this one, so I wasn't too sure. So it's always nice to end up with the correct answer. So that's using a parameterized curve to follow the line segments. Okay, now could we have chosen some other parameterization? Well, this one is going to show us. So it's showing the A part uses t, x equals t, y equals t. Another parameterization that works is e to the t minus 1 for x, e to the t minus 1 for y, and with different limits. Okay, so we're going from 0, 0 to 1, 1, and if you plug in these, you'll see these, in fact, with these limits, go from 0 to 1. So the A part, when you parameterize it with plugging in x equals t and y equals t, or x equals y, we get the answer 3/2. When you plug in the other parameterization, which works as validly, albeit a little bit more work, because the dot product got a little messier, a little bit more to do, but we actually also end up with the same answer, 3/2. So the goal is to find the easiest way to parameterize something, because it makes the calculations shorter for us, and it's going to give us the same answer as if we use a more complicated parameterization. So basically, if we're dealing with circles, trig kind of is the indication of the way we want to go. It'll make it actually easier. If we're going along straight lines and linear functions, stuff like that will be better. if we were following some kind of a exponential curve, then that's why the exponential might be a better pick for that. But as long as we do the parameterization correctly, we end up with the same. We will end up with the same value. Okay, and as you'll see, that's the end of today's lecture. It gets you about halfway through the homework for this week. I'll post as soon as I can the section 18.3 and 18.4 and have those ready at least by Friday. But with my schedule this week, it's gotten kind of crammed. But I will do it early tomorrow morning. So my goal is to by tomorrow morning have 18.3 and 18.4. If you want to take a look at those, and you have through the weekend, actually all the way through till next Wednesday, and then I think we have one more section after that. Remember, if you are planning to take the makeup test this Friday, please send me an email. I'll also put an announcement to that effect in LoudCloud. So then I have an estimation of who's coming, and when we get started on everything, we can all make that makeup test work. Okay? So test 2, makeup this Friday. If you've already taken the test and you do not need to come to class on Friday, but do watch the videos that I post and continue working on the rest of the homework that way. If you have questions, please feel free to contact me through email is always best, because I can see those separately and actually respond to them. If you do go through LoudCloud's forums, I still do get those. I just have to log back into the LoudCloud, and which is fine. I'm happy to do that and answer you through that. But again, email, that works really good for me. Thanks. Have a wonderful rest of the day and take care.